hello everyone. Good afternoon, good morning, wherever you are. We're very happy that you're here with us, and and we're very excited for this. Even if the year is ending, right? It's already on 21st of December, but we're happy that you're still here with us, and we will end the year strong, as they say. All right. Before anything else, I am Jabez Aison. I'll be the host for today, and I am the director of operations here at One Quantum Philippines. You can use the chat if you have any questions, and we encourage you to participate actively, and don't be shy and ask away. Okay, so before anything else, I would like to ask, how are you today? You can just type on the chat box one if you're just happy that you survived the week, or it's still Thursday, but you're just happy that you're still here. Type two if you're chill, and type three if you're excited for the Christmas and for this program for today. Can we see some chats? Oh, we have some two, some chill, one and three mixture. Still checking quizzes and final exam. Oh wow. All right, all right. Hopefully you can get those done before before the season or before the holidays start. There's one. You're just happy that you survived the week. Yeah. I relate as well, and I'm really excited as well to have the vacation. Aside from that, oh, there's one that's super chill. What's your secret to be that chill for today? But anyways, these sessions would just be they're not gonna be super, I should say, formal. It's just us friends getting to know about a new technology, which is quantum computing. Hopefully you won't be drained throughout this session, but instead be energized and see the possibilities with this new technology. All right. So for today's agenda, we would have some welcome remarks and a little bit about One Quantum Philippines, an overview of the course outline, and then we will start with this session propers with fundamentals of quantum computing, and of course a Q&A session afterwards, a small break, and then another session for fundamentals of math, fundamental math in quantum computing and such. All right. So to start the session for today, I would like to call on Sir Jason Victoriano to give us welcome remarks. Hello po. Good afternoon.
Okay, good afternoon, everyone. So I would like to uh, flex my T-shirt of Quantum, courtesy of Sir Bobby. Thank you. Okay, so kanina wala akong nakapolo lang ako. Then it's so happy nakita ko si Sir Bobby nakaganito. Then I changed my so
Salamat.
first time ko nagsusuto, and I am very much grateful for this pair of shirts and polo. Thank you for this. Okay, anyway, thank you for good afternoon, everyone, and thank you for coming to the BulSUQuantum Lift. This is the first Bulacan, first initiative of the first quantum computing for educators and researchers. So I see some of uh, unfamiliar name, but definitely most of the participants are from the four campuses and for the one for main campuses. So I just want to mention their name. Uh, uh, we have Christopher Cunanan from the College of Engineering at Bustos Campus. So is Sir Harris de la Cruz. He's from the College of Science, Mathematics Department. Sir Gab Galang from this CICT main campus. Sir Jess Gueco from Hagoni campus. Sir Jess Gueco also focusing on automation. Sir Gab on IT. Uh, Mary Rose Kagampang, math. and from Sarmiento campus, who is also a faculty of IT and data science. Ma'am Mary Rose Columbres, also from Sarmiento campus, which is in San Jose del Monte, our department head in IT and data science. Sir Michael Mabanta is from the Meneses campus, specializing in information technology and web development. Sir Eugene Perez is also from the San Jose del Monte Sarmiento campus. And I think yung iba ay hahabol because siguro baka man nag-ano pa, nag nag-grocery pa or naghahabol ng ano. But anyway, so we have 2 days intense, actually hindi pala intense, sorry for this, no. So it's an introduction of quantum computing fundamentals, and I think math ba to, Sir Dylan, or Python fundamentals? Um, and ayun, so I just want to to relay yung pinagdaanan namin nila Sir Dylan and Sir Bobby in applying for this uh, for DOST na ito ay i-apply. So last year we applied for DOST retool. So retool is a a program of DOST shared to help the institution to help and to capacitate yung mga faculty ng mga universities. So RITUL stands for Researchers on Industry in Energy and Emerging Technologies, opening opportunities for learning. So yun po yung program. So this is funded by DOSTP Shared. So at ang kataya po natin is One Quantum Philippines. So all the trainings, all the lecturers ay mga galing sa kanila. Tapos tayo po as from the Bulacan State University ay will undergo sa training. So after these 2 days, I think January we will have a intense 12 meetings, 12 series of training na yun na po yung ating kailangang pasukan. We have this uh, uh, one quantum prepared for the topics na talagang matututo tayo. And I think we have also planned, this is only the first phase of our quantum computing initiative. So I think after this, I hope that we can have a proposal, and of course we can have other cutting edge proposal and research with regards to quantum computing. So again, thank you po sa pamunuan or sa officers and board of the One Quantum Philippines, kay Sir Bobby, kay Sir Burns, Sir Dylan, and all of the officers. So thank you po, and enjoy our training, our workshop, and magandang hapon po sa inyong lahat.
Thank you po, Sir Jason. Ayan. Okay, at this point, I would like to call on Sir Bobby Corpus to introduce us to One Quantum Philippines and to give us an overview of our course outline.
Thank you. Yes, so let me just share my screen. So magandang hapon sa inyong lahat. Yeah, so yung One Quantum was it started way back in 2017 as Quantum Computing Philippines, and then by 2021 the DOST approached us, no, in kasi that time they were calling all the physicists, anyone working on quantum technologies, to set the quantum technology roadmap, the Philippines. So they also invited me as part of the industry. By 2022, um, the One Quantum Global community, they wanted to set up a One Quantum community in the Philippines, but then they discovered that there's already an existing quantum computing group. Kaya they approached us, and then they said if they asked if we can just be that community for them. So so that's why we renamed ourselves to uh, One Quantum Philippines. By by early this year, um, ano, they the Fisher gave us a seat dun sa quantum technology board ng Philippines, whose main job is to take a look, review the
Recording in progress.
review the Philippine quantum computing or quantum technologies roadmap. No? So anim kami doon, kasama na yung ako, si Henry, which is also part of our group, Henry Adorna, and Dr. Franz De Leon from DUST, Dr. Sarmago of NIP, and Dr. Jackie sa Romero, sa I think is University of Queensland. So, so simple lang actually yung ano namin. Yeah, so yung mission talaga ng One Quantum is to uh, I will just ano lang locally, no? Ano ba talaga yung gusto namin mangyari? We want to increase awareness of Filipino people sa quantum technology, and also as much as possible introduce it as early as possible dun sa child's education. So to that end, no, so may mga we we partner with different organizations within the Philippines and also abroad, no. So dito sa Philippines, we have a MOA with ASTI. So dito sa picture na to, yung isa dyan, that's Dr. Franz De Leon. And this one here is Jeff Borot. He's also a member of One Quantum Philippines, and he is the team leader of the quantum computing simulator in advanced science and technology. Yeah, so para naman sa for children's education, we also partner with another person in the UK, no. Very interesting yung ginagawa niya because she is teaching third graders about quantum technology na. So may pinakita sila sa amin na children already able to explain at least in high level ano yung quantum, ano yung cryptography na. So really interesting. Yeah, so so initially yung ginagawa namin was to have meetups, regular meetups, at may marami na kaming na gawang meetup actually, which is recorded in YouTube. So this one here is Nardo Manaloto. He's going to be our partner na ang plano namin is to bring a international quantum computing conference dito sa Philippines next year. That's our big goal. Tapos ito naman si Dr. Jackie, ito yung sa University of Queensland, which is also part of the quantum group. And yun, so and we were invited dun sa Singapore, no, to be part of the panel. And this is the kind of international conference that we plan to hold next year. No? It's really about experts in the field, no, local and abroad, and also business people. Bring them together so that the business can understand and also embrace quantum computing. Ngayon sa Philippines, wala pa ako narinig, no? Unless siguro yun yung mga Accenture or Deloitte, no? Which are doing quantum computing, but not in the Philippines. It's abroad, no? So yung ano namin is really to make the businesses aware, no? Para at least ma-build natin yung pipeline natin for quantum enabled uh, Filipinos, no? And in the future, they will hopefully get jobs on quantum computing and based here in the Philippines. And our recent activity, which we did last November 20, ito yung hackathon. Turns out it's actually very hard to. It takes a long time to plan that, no? So took about 7 months in the making, and because the thing is, no one really knows about quantum computing now. So I mean, it's not as easy. It's also not. I mean, it's not easy to teach ba. Ano, I mean, mataas yung kanyang mataas yung kanyang learning curve. So kapag, for example, magpa-meet up ka, most probably konti lang talaga yung less than 5, no, yung darating. Only those who are really interested, no. And ang ano namin is although we are so we are part of the One Quantum Global, but we act locally. And yung by acting locally, we are able to have a much better impact, no? Kasi marami namang quantum computing na quantum computing na mga sa abroad, no, mga programs that you can join, no? Pero at any given time, no, konti lang yung Filipino na nagjo-join doon. So for example, swerte ka na pag may 10, no? Pero yung ginawa namin doon sa sa Cebu, ano yan, no? So we had 250 participants, but mga 95 talaga yung constant na nagpapakita every Saturday. So we do this 7 Saturdays. And the culmination is a hackathon. So ito yung mga participants from different schools, no? Mga estudyante. And we are happy to say na meron tayong mga 95 ka uh, ka uh, estudyante and also instructors who are now able to create quantum circuits, no? And run them on quantum simulators or quantum computers. So yun. Yes, actually, yun lang yun. So quantum computing. So John Preskill is actually a famous person in the quantum computing world, no? And tapos itong kanyang quote dito is it's something to do with quantum computing is about computation in parallel universes, parang ganun. So it depends on how you interpret quantum theory, no? Marami kasing maraming interpretation, and one of them is when you do quantum computing, you're actually computing in different universes. But that's just one of the interpretation. Yeah, so that is us, no? That is One Quantum. And next year, marami din kaming gagawin, and definitely itong pinakauna naming priority is the Bulacan State University quantum computing lecture series na. Okay, so let me now share yung overview ng ating course na. Just share this. Okay. Now, don't mind the dates now. Kasi we're still trying to negotiate if we can do it on a Saturday, no? Yeah, January 8 kasi lahat yan, puro Monday yan eh. Yeah, so it's composed of 9 modules, and each module is ano siya, no? Well, actually, it depends. Uh, may mga may mga module dito that span only one Saturday or 3 hours. Um, sorry, not necessarily Saturday, no, pero 3 hour na ano synchronous online, and another, and there's a asynchronous component, no, which is where the participants are going to um, do some exercises. So module 1 is all about introduction muna to quantum theory, and then yeah, so Burns is going to Burns, which is here also attending, is going to give a more of a conceptual introduction to quantum theory, and ako naman, I will be helping him, providing some mathematics into it. Tapos Elmer is going to give us um, a run through of the mathematics needed, no, sa quantum computing. Um, well, yung quantum computing is mostly, kung theory lang ang pag-uusapan natin, no, it's mostly ano talaga, linear algebra. It's the operation on vectors, tensors, no. Pero you cannot really, if you want to apply it to other things, you have to learn. We also need to introduce, um, in addition to linear algebra, mathematics, like for example yung sa number theory, no, which yung gagamitin natin sa um, factoring, sorry, the Shor's algorithm. So, and dito naman sa sa third module, or the third session, we are going to give you some a review of what's complexity theory, um, so that we will appreciate what's the advantage of doing quantum and doing classical. And then we will introduce the a library called Qiskit. Okay, there's a lot of libraries out there that you can use. No, so sa Google or sa IBM, it's called Qiskit. In Google, it's called Circ. In Microsoft, it's called Q Sharp. But all of them are they all just use the same concept. Kaya we can probably standardize on Qiskit na lang, or depende sa minsan kasi itong Circ has a better visualization. Kaya, but the thing is, the concepts are the same. Kaya yun yung maganda doon. You can just pick whatever framework that you want. And then sa module 4.1, we will talk about itong mga tinatawag na entanglement. So there are ito yung mga concepts sa quantum theory, no? So superposition, and then we have quantum tunneling, and then we have entanglement, no? Measurement. So these are the things that we are going to discuss, and also teleportation. And then we are going to discuss our first quantum algorithm, no? So these are the algorithms na you will realize na mas mabilis talaga yung there's a parang magic na ginagawa yung quantum computing, whereas compared to a classical. So like for example, itong Deutsche Joshua algorithm, no? When you do it in the classical world, no, it takes about exponential time to compute. a certain problem, but with quantum computing, only takes one invocation of that function, and then you get the answer. So that's really, really exciting. And uh, and then and then this one here, we will discuss about quantum searching. So one of the there are two very important algorithms in quantum computing. These are the Shor's algorithm for cracking the RSA and elliptic curve, and also this one here is Grover's algorithm. So Grover's algorithm naman, this is the algorithm you use to find a needle in a haystack, no? And ibang klase yung kanyang algorithm. It's actually rotating a vector. It's rotating a vector so that you can find what you're looking for. No? So, and then so there, Jeff will also explain. So this is like the brute force approach in quantum computing. Usually kapag brute force, di ba, ano yan eh, if there are n elements, then on the average you get, you have to execute n over 2, no? Or in the worst case, n, and yeah, n iterations of your function, no, in order to, for example, find something in this case, no? But with Grover's algorithm, it takes only about square root of n, no? So which means na if you have a million, if n is 1 million, then square root of that is 10,000 lang, no? So yun yung ano, and that's also one of the ways you can attack encryption, no? Through brute force. Yeah. Now, yung encryption na ginagamit kasi natin, yung mga sikat ngayon, no? Ito yung mga tinatawag na RSA, no? So, Rivest, Shamir Adelman, ito yung factoring a very big number. So for example, 2 raised to the 2048 takes about 300 trillion years to factor, no, to crack. But with a quantum computer, there's already an algorithm to crack that, no? Takes only about a few minutes or seconds, no? So ito yung Shor's algorithm. We're going to discuss that, and it's actually quite a long topic because we are going to discuss talaga ano ba talaga yung how do you encrypt using RSA, no? How do you encrypt using elliptic curve? So elliptic curve was also one of those encryption na sikat ngayon, no? Kasi konting ano lang bits is required in order to have the same amount of encryption power, no? Sa RSA, kaya yung ginagamit ng ating mga mobile phones, no? Because they are low powered devices, yung elliptic curve. And elliptic curve is also being used doon sa ano, pag sa blockchain, no? Or sa mga Bitcoin. So yeah, so that's already ano na yan, no? That's already a red flag, no? Ano na yan? Once we have a fault tolerant quantum computer, which they estimate to be in 2038 or 2039, no? Ano na talaga, vulnerable na, no? And even right now, no, na wala pa talaga yung fault tolerant quantum computer, error corrected quantum computer, no? But since we have the theoretical in theory, it can already be, there's already an algorithm, no, to crack this kind of encryptions. Yung mga ginagawa ngayon ng mga nation state is to, collect or harvest and decrypt. Harvest now, decrypt later. So yung ginagawa nila, no. Kaya nung May 4 of this year, naglabas yung yung government ng US, no, na they require na yung deadline for all government agencies to give a inventory of all the encryption na gagamit nila May 4. And they are going to now switch to what is known as post-quantum cryptography. And then, so that's just one of the, that's just one of the application of quantum computing now. And the other one, which is also very interesting, is itong optimization. Like, for example, solving yung mga, yung traveling salesman, no? Traveling salesman. Um, so any optimization actually, no? Uh, as long as you can cast it to what is known as quadratic quadratic unconstrained binary optimization, ano siya, pwede siyang uh, pwede mong gamitan ng quantum computing. And yeah, so yun yung and in fact itong optimization, ito talaga yung application ng quantum computing sa industry, no? And also the machine learning part, no? Which Dylan is going to give us a lecture with on. And then probably I can ask probably Dylan if you can explain module 9. That's okay.
Yeah, sir. Actually, I would like to tackle this after we talk about the research directions of my talk so that,
Okay.
you'll get try to be excited on module 9.
Okay. Thank you. Yeah, I think that's it for me, Jabez. I'm gonna unshare my screen.
Okay. Um, just a second. Sharing my screen. There we go. Okay. Thank you for that very in-depth overview, Sir Bob, and hopefully everyone is excited for the sessions to come. And yeah, please don't be overwhelmed. And yeah, don't worry, we got you. And yeah, we will provide everything that you need to get started on those areas that Sir Bob discussed. Okay, so without further ado, I would like to give the floor to Sir Dylan Josh Lopez, the Director of Education and Collaboration here in One Quantum Philippines, for our first session, the fundamentals of quantum computing. So maybe you can introduce yourself a bit, sir, and then yeah, um, uh, go ahead on the session.
All right. Yeah. Thank you, Jabez. Thank you, Sir Bobby. I just want to confirm that you can hear my audio loud and clear.
Yes,
Hi.
sir, loud and clear.
Great. So yeah, hopefully everyone's still here. Don't worry if you don't understand some of the terms earlier. That's the point where we're doing this. And for those who are not in of the BulSU Retool program, don't worry. We do have other workshops or lecture series that would help you get to know quantum computing more and what are the specific applications that you might want to do. So, without further ado, let me introduce my topic. So let me just pull up my screen. Where is my screen? Okay. Mhm. Sharing my screen. Here we go. All right. So hopefully you can see my screen now. So great. So allow me to introduce you to quantum computing. Oh, sorry. This is a different slide. Let me just stop sharing first. Different presentation. Sorry. This one. No. Yeah, sorry. Too much presentations for a day. Okay, let me share again. Right. Aha. Right. So allow me to introduce quantum computing as something, a new technology that you might want to play with, especially if you want to do research. So this is the first webinar out of the two introductory ones, and we'll have several modules on the next year. So yeah, allow me to just go through the basic, not actually the basics, the overview of quantum computing and why should you be excited about it. So next slide, please. So yeah, I'll go through with the overview of quantum computing. What is quantum computing? The limits of what we have right now. What are the efforts nationally and globally of quantum computing, and how and why should you be interested in investing your time in doing quantum computing right now? There are many ways to do quantum innovation, and that is through research, and we'll discuss about the topics that you could do and how could you actually start doing quantum computing? And what are the expectations for the next modules to come? So, allow me to introduce now what is quantum computing. Now, I believe most of us are in the computer science and or technically just in the computer field or information technology. We know what Moore's law is. It is the economic observation that we're cramming many ICs into a chip every year. It doubles and now it's actually exponential, but we are at a limit. There are many articles saying that Moore's law is already dead, and let's see why. When we try to cram integrated circuits into a chip or in a specific construct, we are trying to make it smaller. And as we go smaller, it is going towards the limit of particles or subatomic particles that we have right now. And right now, IBM has already introduced a 2 nanometer chip. If you can't imagine how a 2 nanometer object is, it is even finer than one of our hairs. And imagine that if we could make things a lot more smaller, it could even go to the size of an electron. And right now, 2 nanometers is not that of a problem for one electron. However, for those who are familiar a bit of quantum mechanics, if you or nanoelectronics, there is a concept called quantum tunneling. If we have a certain object blocking the path of an electron, or what we call a potential barrier, it may, in a certain probability, can pass through that specific blockage. Now, why would that matter? What's in it for us? Imagine instead of an electron activating a certain transistor or a certain bit in your chip, it's going somewhere else. It's wandering through another piece of space. Now, that can pose security problems or even just basic logic problems. Instead of activating a one, it might not activate at all because the electron is not flowing there. So, if we try to move in that kind of direction, classical computers, or right now, the regular computers that we have, might not work properly if we push really the limits. Okay. So what we need to find is either we buy more computers that are not moving towards quantum tunneling or in the very nano electronics, or we try to find a new way of doing computing, which is quantum computing. Now, if you can't beat them, join them. So if you can't beat quantum tunneling, make use of quantum tunneling in your computing. And it is very useful in many ways. Actually, I'll be discussing that once we talk about optimization. It is a fundamental concept to find a global minima. For those who are doing machine learning or calculus, it is an important concept to find the global minima of a certain function. Now, going back to quantum computing, it is a new type of computing that uses quantum mechanics as a basis on computing, storing information, and processing information. So don't worry, if you don't know quantum mechanics, you can still survive in being a quantum programmer. So it is just fundamental to know some of the basics that we'll teach you in the next few weeks, that it is not that scary. It's just really linear algebra. So, in a nutshell, quantum computing, again, uses quantum mechanics to represent data, perform logic, or even formulate algorithms. And I'll be just going through some of these key terms in quantum computing that you might need to be familiar with, especially when we go through a lecture series. One is the concept of a qubit or a quantum bit. Now, in classical computing, we have bits, right? Or when I say classical computing, this is what the regular computers that we have right now. And a quantum computer is, quantum. It relates to classical physics and quantum physics. But in this case, okay. So a qubit is the bit or the basic information of a quantum computer. In a classical bit, it's either 0 or 1, on or off. There is 5 volts or no volts at all. It's activated, unactivated, true or false. That is a bit. And for one bit, it can only hold one piece of information. And that's what we know so far. If you have 2 bits, then you can hold two informations, the 2 pieces of information. But in a qubit, you don't represent it as 0 or 1. You can actually represent a qubit as a vector or a list of numbers, primarily 2. So in this case, you can have 0 and 1 at the same time in that specific qubit. So it can hold 2 pieces of information. So one qubit is already 2 bits. So can't you make hands? I shall be making gestures. But if you have a qubit, 1 qubit, it actually acts as 2 bits already, 2 classical bits. So if you have 2 qubits, you have 4 classical bits. And that's amazing. That means you have 2 raised to n more efficient qubits in representing information compared to a classical, byte or classical register. Now, another thing is that qubits are not confined to having values 0 or 1, either 0 or 1. It's not mutually exclusive. It could be actually that a qubit could have 0.5 and 0.5 possibilities of 0 and 1. So it can be both at the same time. It could be 70% 1 and 30% 0. It is what we call a superposition state. So it means that there is a superposition of values that is represented in a certain qubit. That means you're now also representing probability in a certain qubit. It's not just 0 or 1. That gives us a lot more computational advantage since we're working with probabilities instead of solid 0 or 1. Now you might ask, what do we do with the other math that we're doing with logic circuits so far? There is actually a way to do that, and we're going to talk about that in the next year, because we have what we call a quantum circuit. Don't worry, you're not going to be Doctor Strange and create circuits in the air, or Tony Stark moving around those things. You can actually form a quantum circuit without soldering anything. You just need to have math. Now, there is another concept called entanglement. Now, I'm not going through the mathematics or the quantum physical aspect of entanglement, but imagine this is a bit more romantic. Imagine 2 qubits at one point in time, they meet together and they have that certain connection to one another. And then you try to split them apart, let's say 5 kilometers, 10 kilometers, 100 kilometers apart. They will still be connected through somehow a magical thing. Well, Einstein doesn't believe in that in the first part, but it's called entanglement. Entanglement, when you try to enact on one qubit or one particle in another point in space, and you do an operation, maybe spin it around or add 1, add 2, it actually affects. There is a direct correlation that the other qubit, there is a reaction already without you touching it. It's entanglement that's working there. Now, you might think it's magic, but it's not. It's quantum physics. But we're not going to discuss that now. This is more of a bit later in the lecture series. We're in how do we take advantage of this natural phenomena, this natural correlation of values without you computing anything. It just happens. How do you take advantage of that in algorithm design? Okay, that's something that you might be interested about, but we're going to talk about that later. So here's a summary of what I've been talking about. In classical, bits could be 0 or 1 at the same time. It could not be 0 and 1 at the same time. But in quantum, you can. It's called a superposition of values. That means you can be 0 and 1 at the same time with a certain amount of probability. Memory now is more efficient in quantum computing since you are representing two raised to n more efficient representation of bits or information compared to a classical computer. In operations, you might do, logic circuits or just Boolean algebra, and you can actually do that in quantum computing using linear transformation. And you can also design what we call a array of numbers, and that could define a certain problem that you have, especially in optimization. And but I'm not going to discuss that so much. But it is an amazing way of how to represent graphs or matrices so that you can do fast optimization. Okay. Now, there is a limit to this, or rather not a limit, but there is a difference between and how do you do quantum computing based on hardware. There is analog quantum computing and digital quantum computing. Analog computing, it just uses the flow of quantum mechanics to solve a problem. There is, you can create qubits out of the regular way in superconducting qubits, and you try to manipulate them so that they could react to the problem that you have or an algorithm that you have. But you cannot correct errors made by these qubits. By the way, there is a concept called decoherence in qubits. That means as you evolve through time, the information that qubits becomes corrupted or it becomes erroneous because it could not hold that information. You need to keep it in a certain condition. And some of the quantum hardware requires it to be in the superconducting level. That means it should be in a temperature near 0 Kelvin. So you need to be very careful so that it could retain that information. Now, if you suddenly, pull up the temperature, the information might be lost because the orientation of the qubit might be different already. So that's something that we're going to talk about in the next physics part. There is digital quantum computing where we solve that problem by having what we call control units, just like regular computer hardware. And we use that way so that we can efficiently hold coherence, or we try to correct the error after, determining the measurement or reading the data from the qubits. Okay. Now, there is what we call quantum advantage. Now, not every quantum algorithm is better than a classical algorithm. Quantum computing is not here to replace classical computing in what any way. There is what we call a significant advantage, such as Sir Bobby mentioned, Shor's algorithm in cracking the RSA encryption. So in this case, one is the application of RSA encryption, but it's primarily on prime number factorization. Wherein you can do factorization using Shor's algorithm, which is log of n3 or the cube of n more efficient than a classical algorithm. That means instead of computing for 1,000,000 years for finding your password, it could only take 10 minutes for a quantum computer to solve. That's amazing and scary at the same time. Another one is moderate speed advantage, is exemplified by Grover's algorithm, or generally any phase estimation algorithm, wherein given an unsorted set or database, you're trying to find a certain value. Now, at the worst case scenario, you are going to have a complexity of n. That means if you have 100 points in your data set, worst case scenario, that the person that you're trying to find is at the end. You need to do a brute force, and that takes a for loop of size of n. But in Grover's algorithm, if you do phase estimation, it only takes square root of n. Instead of having 100 iterations, you only need 10 to solve or to find that missing person in your database. And it could also be not in database application, but also in estimation, generally in estimation or, expectation computation in statistics. Another one is in adiabatic computing. This is something that we need to note for optimization. Wherein, if we have optimization, if you're doing operations research, then you probably have encountered Cplex, Gurobi, or even Excel. So sometimes that can be better than classical computing. But if you try to expand or increase the number of continuous or number of variables in your optimization algorithm or number of factors, it becomes it's more expensive to do. It takes longer in classical computing or Excel. But if you use a certain kind of algorithm, for example, adiabatic computing, it could actually be stable or even efficient for larger problems. And we're going to talk about that more in optimization theory. Now, I'd like to talk about the whole spectra of quantum. It's not actually just quantum computing, it's just one part. There is a whole broader field called quantum information science. Now, quantum information science encompasses hardware, software, and communication. So, quantum hardware, we create devices that uses quantum mechanics to determine values. I'll show an example later in quantum sensing, where it uses quantum mechanical principles to find certain things in the Earth or even measure values using quantum computing. There's also, if you want to create your own quantum computer, that's also part of developing quantum hardware. Quantum computing encompasses a lot of things. It could encompass quantum algorithms, quantum optimization, quantum machine learning, quantum cryptography. All of those fall under quantum computing. Now, there is an overlap between quantum hardware and quantum software, which is quantum communication, wherein you develop the quantum internet. Now, what is that? The quantum internet is unlike Web 3.0 or 4.0. Quantum internet makes use of quantum computing and quantum hardware to efficiently deliver secure data over a quantum network. There's a lot of quantum in that sentence. But the idea is that quantum communication provides a secure communication between you and another user, even without direct media. You cannot be hacked in a quantum internet, theoretically, since you are using the concept of entanglement and even quantum teleportation. Quantum teleportation is that you have information in one end of the world, it vanishes, then it suddenly appears somewhere, probably in the US, where it's the endpoint of your communication network. Now, if you want to know what's going on with that, Jabez will talk about that in quantum teleportation. But another one is cryptography. If you are working on a classical network, the regular internet that we have now, you can still secure information through cryptography, just like using a quantum algorithm and post-quantum cryptography, so that people will not hack your data. Now that's an overview, but there's a lot more technicalities to that, and we can talk about that more in the next few weeks. So, what is quantum computing right now? In the world, we are investing a lot of money. As of 2023, we have 38.6 billion US dollars as an estimate of investment in working with quantum computing. In the Philippines alone, has approximately 860 million pesos. So, if you're in SUC, where would that fund just go if it's just in quantum computing? There's a lot of opportunity for research and call for proposals in the next few years. We have this retool program. We have a lot more things to do. We given that amount of money just for quantum computing. There is a big opportunity for us to do research and increase our capability in doing these kinds of research or innovations. Imagine you can even have more budget compared to other countries in the EU. So it's something that we should be proud of and should be grabbing given the opportunity. Now, I'm presenting right now is Picard's roadmap, the UST Picard's roadmap for quantum computing or quantum technology. We are in track. Actually, we are a bit on track in terms of capacity building. We are now building your skills to become capable people, researchers, educators, to do quantum computing so that we'll provide this new technology for the country. Imagine you are the pioneers right now learning quantum computing, and you will be teaching this to the next generation. Imagine that. You are probably one of the first people that would have formal capacity building in Luzon or even in the Philippines. So I hope you're proud of that. And Sir Jason is very proud of that. So, you people, actually, we are in a very good time to learn quantum computing to contribute for our country. Okay. So, there's a lot of things to unpack, but one of them is we are in a very big constraint era, which is what we call the NISQ era, or noisy intermediate scale quantum computing era. I'd just like to give you this overview since we are not yet in the fully idealized state of computing. It's not as mature as AI. It's actually, imagine we are now in the 1980s or the 1970s that ENIAC has just been released, or even before uh, 1980s, before the personal computer has released. We are in the age of Jack Kilby introducing the first electronics that we could do computing. In that early, we can still know what to do, and we can prepare all of the innovations right now since we have simulators. So in the NISQ era, it tells you that we still have a scarcity of qubits out there. Qubits are not naturally made. We still need to make them in a very simulated space or isolated space so that they could work. So we need more physicists and experimentalists, engineers that could do quantum engineering as well to make more qubits stable so that we can do efficient computing. I talked about coherence a while ago, and here it is. So not everything that you're going to create in quantum computing would have 100% advantage. I'll just leave it at that. It's not the holy grail of emerging tech right now. As it is emerging, there are still a lot of bugs. We are pre-alpha stage, if you know, if you're in development in terms of quantum computing. But it shouldn't stop us in developing innovations right now because we don't want the AI situation in the Philippines to repeat itself. We need to be a bit ahead of our time so that we can have innovations ready for the next generation. So why do you still want to do quantum computing if it's still buggy, if it's still not good? So I hope you're familiar with the history of AI, wherein it started way back in World War II. If you watch the Imitation Game, and there was a lot of interest that in that time, but in the 1970s it stopped because the limits of hardware could not help or could not does not have the capacity to work with the algorithms at that time. So people think that AI is going to die. It's not worth investing. Until in 1980s, we had the personal computer where we can do a lot more computing, but it's died out again because neural networks were a thing in academia, but there's no hardware that supports or does very good way in computing neural networks until we have 2012, 2013, where we had the GPU, wherein, if you're familiar with AlexNet, it solved the ImageNet problem by using GPUs. One of the first implementations in using a GPU as a computational device for solving AI. And then everything's history. Now we are in the age of booming artificial intelligence. So if quantum is just the same as the idea of artificial intelligence, knowing that in the future it would happen, it just needs support of hardware, then should we stop doing quantum computing? No. We know that the hardware is being built and there's a lot of investment research going on, and we know it will work. Theory tells us it will work. Therefore, we as humans, as believers of science, we are pushing the limits of that. And we know it will happen, just like with AI. We don't have to have a winter. We just need to believe that we can do this, even if we just need to ready the algorithms that we have right now. And once the hardware is ready, we just plug and play. And that's okay. Okay. So that's where we start our innovation. Now, talking about that, let's talk about some of the things that you might want to do if you are into the quantum technology or the quantum realm. If you want to do hardware, if you really want to, into computer systems and you're into physics, I urge you to do quantum hardware. If you want to create the first quantum computer in the Philippines, be my guest. There are a lot of ways to do this. There's not one way. We're still searching for the best quantum topology out there that could work with the hardware. There could be superconducting loops, trapped ions, quantum dots, so much more. So we're not going to dive into this, since this is more of the quantum physics side, um, really outside of quantum computing. But hopefully, we'll have a talk about this in the next year so that everybody could know how could we actually do quantum hardware. Quantum sensing is the interesting application I'd like to show you. It's actually a startup in Singapore wherein they use a quantum sensor. This is working, by the way, that they put it in a car, the quantum sensor. It tries to find fuel reserves or oil reserves under the earth and even under the sea without, drilling. And that's actually very good. That means you don't have to waste money in drilling everywhere just to find where our oil reserves. You just need to have this machine. So that's one application of quantum sensing. There can be even more. Quantum communication, this is the quantum internet. Using quantum hardware, you can even do efficient communication without, physical wires. It's not even, it can be a bit wireless. But the idea here is security. You don't have you're secure with the network because the quantum mechanics will work on that, and people will be very challenged in trying to decode quantum information and even trying to get all of those things in the atmosphere. I'd like to note here that there is I have that slide later, so I'll talk about that later. Sorry. Quantum optimization, if you are into operations research or you're more in the industrial side, quantum optimization helps you to formulate all of the classical algorithms that you have in optimization that could work on quantum computers. Sir Bobby mentioned the traveling salesman problem. There's a lot more. There's also the bin packing problem. There's also supply and demand problems. Supply chain problems are also applicable in quantum optimization, even transport problems. So that's something that we can talk about for applications later. Oops, sorry, there's skip a slide. Of course, quantum machine learning. There's a lot of ways to do quantum machine learning. One is use quantum computing to optimize machine learning, use machine learning to optimize a quantum algorithm, or you can do a hybrid machine learning algorithm that makes use of quantum computing inside so that you can have better results or even converge faster. And don't worry, we're going to discuss details on that and how to apply this practically on, let's say, your regular data sets, such as, let's say, MNIST and even CIFAR. So those are the hello worlds of AI, remember? So we're going to do that in quantum as well. How do you do QML, and how can you make it useful in industry? So let's talk about applied applications rather than the whole spectrum of QIS or quantum information science. In the life sciences, using quantum optimization algorithms, you can use it to do drug design. And drug design is very complex for a classical computer to do because it's a combinatorial optimization problem. That means you're trying to find all the combination of the possible chemical compounds or even the proteins so that you can find better compositions. That's very hard, and that if you have a lot more things to combine or to compute with, it takes exponentially a lot of time. So, but if you use quantum computing, it could actually shorten that to even in a logarithmic scale or even an exponential scale. So there's a lot of applications for this. If you have partners doing drug design, quantum computing is one of the leading technologies right now in finding good answers. Finance and economics. There is a very large field of quantum finance, of using quantum computing for finance. One of them is forecasting. Another one is for derivatives and risk assessment. And there is also for estimation expectation for large scale, what do you call that? For large scale derivatives and time series analysis for, let's say, stock prices. So you can use quantum computing to understand the time series data better for a given stock. Okay. For security, this is something that Sir Bobby will also talk about. Is quantum cryptography. You can even use the quantum Fourier transform or even Shor's algorithm to find out you know how to decode the RSA encryption. There's also quantum key distribution where you use quantum computing so that you can manage all of your security aspects. Pattern recognition uses artificial intelligence, of course, to do classification, regression, even anything that what AI can do right now. You can add quantum into it. I'm actually in the electrical engineering field, and you can even use quantum computing for optimizing power grids and even doing state estimation and even a lot more. For those who are in the industrial engineering, this is what I'm mentioning earlier. You can even do, traveling salesman problem or bin packing problem. This is a 3D cargo bin packing problem on your right. So this is a very interesting topic if you are working with logistics. There's also in the transportation side, and one of them is traffic management. So if you have problems in traffic, well, the Philippines does. But if you're working on a traffic research, that's something that we can apply quantum computing with, especially, for example, how do we set the proper timing or which traffic light should we turn on and off, or the series of traffic lights on and off, so that we will have efficient flow of cars. That's something that you can even formulate in an binary optimization problem and put it in quantum computing. That means a quantum computer could even help solve probably Philippines traffic problem. But take note, nobody has done that yet. Probably one of you might do that, and we'd love to help you with that. Communications. There's a lot of things in the logistics side of communication is cell tower placement problem. So this is another Kubo problem or optimization problem in quantum. You can do that. Now, this is the interesting thing I want to talk to you about is you can even design a quantum communication device that could send data using quantum teleportation. So that's a quantum teleportation device, just like in sci-fi. But you can't transfer a person, but only data. There's an interesting research from China wherein they have they use the entanglement theory or the observation. They try to entangle qubits on Earth, then they send one qubit in space using their satellite. Then they try to uh, manipulate the one on Earth, and they observed those who are in space in that satellite that there's suddenly a movement of that qubit out there, but in the but they only applied the operation on Earth. So that's really weird and amazing at the same time. That means that is entanglement at work. There is no communication in between. There's no satellite um, communication going there. It's just pure entanglement. And we can do that given amount of resources that we have. If you are interested in this, um, currently we don't have the skills in One Quantum Philippines in teaching quantum communication in hardware, but we do have partners that could help you in doing that. If you're interested, we'll try to form a group so that those who are interested could have opportunities in learning this in a deeper sense. Now, I'm talking about this all as applied theory, and you probably think that how could we do this? Do we have a quantum computer? Answer is we don't have a quantum computer in the Philippines, sadly. But does that stop us? No. There are a lot of ways to access quantum computers, and you can even access them online. One of them is through IBM. So IBM has a quantum computer already, and we can access it for free online. We just probably need to wait for some time so that our circuits will be running. This is an actual circuit that I made in in the IBM Quantum Composer. It actually shows Grover's algorithm, and we can even run this in an actual quantum computer. Now, if you don't want to drag and drop things, you can even code this in Qiskit, and Qiskit is in Python, and we'll be discussing about that more in the next few weeks. And how do you code this? So there are other quantum platforms out there that uses different types of quantum physics in their computers. We have QERA, we have Quantinuum, Rigetti, Fujitsu, Intel, Microsoft. They have their quantum platforms and how to do that. However, Fujitsu here does not use a quantum computer. It uses what we call a digital annealing unit that is specified only for optimization. Now, if you still want to do good quantum research and you don't want to wait online, you can actually repurpose your current setup. If you have a NVIDIA GPU, RTX preferably onwards, you can repurpose that as a quantum simulator at your own home. You just need to download certain libraries such as what we call QQuantum. And it's really amazing that you can treat your own GPU as a quantum processing unit or a QPU. You can use it for quantum machine learning using running quantum circuits, and it works similarly as a quantum computer. So, if you want to work on a quantum algorithm but you don't have access to a quantum computer, you can still do that in your NVIDIA GPU. And if you want to do hybrid algorithms, that means you're using a classical algorithm with your quantum algorithms, just like machine learning. You can do that in NVIDIA CUDA Quantum. So this is CODA in the original syllabus, but since they already updated the name, so this is now CUDA Quantum. And we will be teaching you how to use this in your PC. Now, if you don't have a GPU right now, that's completely fine. We can make use of Docker instead. So we can access NVIDIA's um, hardware for this, right? So that's how we could actually do quantum. And I hope to see you in the next weeks. So I promised I'll be talking about module 9 a bit. So overview, you are going to do a very, very small proposal for a possible quantum research, applying it to your areas of expertise. But I remember um, Sir Jason and I talked about it, and preferably the topic would be on disaster risk management. So if you have ideas on how to do that, we will help you to how to do it in a quantum way so that we can do research readily next year. So I hope you, if you have any questions, I'll love to talk about that after the next slide. So thank you, everyone. So if you have any questions, or if you have personal questions that you don't want to broadcast to the group, I'd love to connect with you through email. I'm on LinkedIn. You can scan this QR code. So nice to meet you, everyone. Hope to see you in the next few weeks. Thank you.
To send your questions in if there are some things that are still unclear to you, or do you have some specific questions already, and you can type them out. Okay, so while waiting, Sir Dylan, I have a question. So if we do have some quantum simulators, or what's the limit of a quantum simulator? Of course, a real quantum computer would still be better, right? At what point do we can we use quantum simulators, and what point should we transition into a real one?
Mhm. So right now, quantum simulators, a bit of briefer for everyone. Quantum simulators are still classical computers. Your PC right now could be a simulator. So they could simulate how quantum computing, quantum algorithms work for your PC. So technically, it's still classical computing, but it uses the idea of the quantum way to solve things. So the limit there is still the number of information that we could put for the computation. So if you expect it to, for example, to scale, then you first want to do it on a classical computer, model it there. Then, if you think it's best, it's already good, then we try to do a try to implement it in a quantum computer if it's available. Now, the limits of a classical simulator is that if you scale it too much, it would not work. So, if it is on the exponential level of representing qubits, then probably it will fail. Another one is if actually we're pertaining to the GPU simulation now, I think there is a limit on the number of qubits that you could work on. For one 3070 GPU, I believe the limit is 30 qubits. So, but that's already a lot of information if you are representing classical information. But it's not optimal for optimization algorithms, where we're looking at a almost 1:1 node for representation. So yeah. So the limit there again, just to summarize, one is the classical limit still. What the limit of the classical is still information representation. So it would tend to be very slow as you increase the size of your problem. And second is if you're using GPUs, there is a limit of 30 qubits. So yeah.
Okay, so I'm not seeing any questions for now. So yeah, let's take a 10-minute break. Oh yeah, there we go. What if our laptop is the usual setup laptop? Can we do the activities of the next phase?
Yes, answer is a very big yes, since your activities would not be very large scale. So that means you can still use your laptop. Another way is we can still use Google Colab, if you're familiar with that. So we can use that to work with algorithms, and they will still work. So don't worry. All of the activities that we'll be giving is not a very large scale implementation. So working with the lectures would be okay if you have your laptops here, or even school computers are still okay. However, if you're planning to do research, that's something we need to request for hardware for. We need to estimate first what's the limit of the research. Then let's look at what specific hardware that we could use for a proof of concept. So yeah.
Awesome. All right. So yeah, going once, going twice. Okay. So don't worry, everyone. You can still send in your questions during our break, and then we can answer it right after, before the second session. Okay. So let me just share my screen. Okay, thank you again, Sir Dylan, for that very wonderful introduction and overview to quantum computing and all of the applications that we can do. And hopefully, as you said, we can jumpstart the research here in the Philippines as well. Okay, at this point, we can take a well deserved 10-minute break.
Good evening, Javis. Thank you. Can you hear me? Am I coming clear? Okay, thank you. Let me just share my screen. All right. Are you seeing my screen right now? Okay, yeah. Good evening, everyone. Esteemed participants and colleagues, and welcome to our introductory lecture on the mathematics of essential mathematics to quantum computing. I'm Elmer Peramo. Actually, I'm wearing two hats. I'm senior researcher here in the Department of Science and Technology, Advanced Science and Technology Institute, or DOST ASTI. I'm also part of One Quantum Philippines. And thank you for tuning in. Your presence here is, although virtual, it's a testament to your curiosity and eagerness to explore one of the most thrilling and one of the most fascinating frontiers of modern science and technology. So today, we're going to embark on this journey to the realm of quantum computing. So this field challenges and expands the boundaries of our understanding. So our goal here is just simple, to whet your appetite for this intriguing subject and to demystify some of the concepts as we dance through the mathematics and quantum computing of this field. So I will use a whiteboard to illustrate some of the fundamental ideas because mathematics. It's better to actually explain mathematics if you're scribbling things. No? So I'm going to use a whiteboard. Forgive my ugly handwriting, and I hope the essence of the concepts will shine through. By the way, during the discussion, you might notice me code switching from between Tagalog and English. Sorry, I apologize to those who don't speak our native language. So, but remember, today's session is just a teaser for our lecture series next year. For next year, we're going to have a more in-depth exploration, and I encourage you to approach this lecture with an open mind and ready to ask questions, and most importantly, to be amazed of the possibilities that quantum computing holds. Okay, so as you can see here, quantum computing lies at the intersection of the physics, mathematics, and computer science. To give you an outline of the things that I'm going to discuss for this two-day teaser lecture, for day one, first I'm going to compare classical computing and quantum computing, and then discuss vectors and matrices, and then later on some motivation. And then on day two, we're going to delve on complex numbers and probability theory. I'm just going to show you some of the resources that you may want, because as you can see, we won't be able to tackle everything about quantum computing. So this is just to whet your appetite. So I really advise you to search for resources. There's a ton of resources online, even for the mathematics. Like for example, here you can peruse the MIT OpenCourseWare, or even Khan Academy for the different mathematics involved. Okay, let me just, and these are the mathematics for what to learn quantum computing would also need basic trigonometry, probability theory, and complex numbers. So let me just go to the whiteboard so that I can explain the concept to you. Okay, sige, to discuss quantum computing, perhaps it's better to compare quantum computing with computing or classical computing. So in classical computing kasi, di ba, we use the concept of bit, or bit means binary digit. No, it's or can be represented as 0 or 1, no, deterministically. So ibig sabihin, we use bit for data representations, for example, dun sa ano natin. So gumagamit din tayo ng mga physical properties ng mga, like for example, if we sa hardware natin, like for example, yung mga different technologies, like in compact disc, di ba, may optical technology yung ginagamit. But basically, kailangan lang natin na ma-distinguish yung 0 or 1. Or for example, in electricity, kung 0 siya or 5 volts. Or kunyari, kung sa, let's say, magnetic tape technology, kung magnetize siya o hindi. So basically, parang, yun yung concept nung bit, no? Meron tayong two states, dalawa state. Now, in quantum computing, anong difference sa quantum computing? In quantum computing naman, we use the concept of qubit. Qubit stands for quantum bit. Okay? So, sa quantum bit, in quantum computing, ang pagkakaiba niya, we can now represent yung ating, we can now use the quantum states, no, to represent our information. Like for example, in this case, a quantum bit can be in an infinitely in a superposition of 0 or 1. Pag sinabi natin quantum bit, so ibig sabihin pwede siyang superposition. This is a term they use in quantum mechanics, but mathematically we can say that it's analogous to the concept of linear combination in linear algebra, no? Parang ito, makikita natin, we can represent a quantum state by this notation, for example. So ito, sorry, medyo maraming Greek letter, pero I'm gonna explain this very iconic equation in quantum computing or in quantum mechanics. So ito ay Ket notation ang tawag dito, or Dirac notation. Pag may makita kayong parang ganyan, okay? Ito, yung parang bahay, tapos meron ditong may symbol dito. Like for example, let's say alpha or beta, or in this case psi, no? This is the Ket notation. Kaya siya Ket or bracket, actually bracket yan eh. Bracket, inimbento nila Dirac, no? Yung Ket, ganito, yung bra naman ay yung baliktad. Parang ganyan, tapos meron ka. Yan. This is bra. So this, pagka-Ket, this is parang column vector. Ito ay row vector. So usually gagamit tayo ng Ket notation. So in this case, Ket psi is equals to alpha, which is just a number or a scalar, times this Ket 0 plus beta times Ket 1. So this is a linear combination. Di ba pag sinabi natin linear combination, meron kang scalar, tapos may vector ka, plus another scalar, tapos may vector ka. So basically, pag linear combination, may multiplication at saka addition. No? So, yung term na superposition, mathematically, is just a linear combination. So, ibig sabihin nito, meron kang mga states. Like, for example, this is one quantum state, this is another quantum state. And, you can represent another quantum state as a linear combination or a linear superposition Ket 1. So, ito yung gagamitin natin laging parang basis vector natin sa ating mga susunod na discussions. Itong Ket 0 and Ket 1. So, yung difference niya, itong bit sa classical computing at qubit in quantum computing, dito, you can represent your data as a superposition of 0 and 1. Parang usually na ang analogy nila dito, yung parang pagka toss coin ka, di ba? Pag nag-toss coin ka, halimbawa, laging deterministic yung lalabas sa sagot. It's either heads or tail. Parang ganun. Heads or tail. Pero sa quantum computing, think of it na parang umiikot pa yung coins. na gano'n. Na unless i-measure mo, hindi mo malalaman kung ano yun, kung heads or tails. So, parang somehow ganun yung superposition. Okay, so yung qubit, so yung mga quantum computers kasi, minsan sinasabi nila kung ilang bits yung ginagamit nilang technology. Hindi ko alam kung ilan na yung pinakamataas na bit na ginagawa ngayon ng Google or ng whatever companies, nasa 26 or 32 or 50. No, but basically, you can extend yung qubit into, let's say, for example, this is a 2 qubit states. Kung merong, ang qubit kasi pwede siyang, ito yung pag 1 qubit lang, ket 0 and ket 1. And then, we can represent all the 1 qubit systems as a linear combination nitong mga to. Parang, think of it as concept of a vector space, no? Based on these basis vectors, you can generate or you can span the whole vector space. So yun for your 1 qubit system. Now for 2 qubit system or for 2 qubit states, syempre we can have 4 possible states. So meron kang ket 00, ket 01, ket 10, ket 11, no? So may 4 ka. And generally, kung meron kang n qubit states, so meron tayong 2 to the n. No? So, tignan nyo na lang yung pattern kung paano nyo i-represent. Kunyari, 3 qubit states. So, we're going to have how many? 8. Tama. Kung, let's say, 5 qubit system, you're going to have how many states na possible? 32. So, 32. So, yun yung representation natin ng mga qubit states. So, since this is computing, we do computation. No, parang isipin nyo na lang kung paano din nag-evolve yung classical computing. We started with, basta binary lang, binary digits, and then also in transistors, vacuum tubes pa pala muna, then transistors, tapos IC, gano'n. Tapos doon, nag-start din silang gumawa ng mga programming language. So yung evolution, parang ganun din, no? Na titinan natin, yung evolution ng quantum computing, parang bumabalik tayo sa, 1950s, mga gano'n. So yung state na, pero marami ng mga quantum algorithms na nade-develop. So basically, quantum computing, parang we leverage on the phenomena or mga properties ng quantum objects, like for example superposition, tas meron pang interference and entanglement, and yun yung mga so we leverage on those properties and take advantage of those. Mamaya makikita natin kung ano yung advantage, what's the advantage of quantum computing over classical computing. And okay, sige, since this is computing, let's do a sample computation. Paano ba ginagawa ang sample computation sa quantum computing? So basically, meron kang mga quantum states, di ba? We represent this. Kunyari ito, yung sa 2 qubit states, let's start with ket 00, okay? So sa ket 00, we apply a quantum gate. Much like the way we do computation in classical computing. Meron tayong mga bits, di ba? And then gumagawa tayo ng circuit, di ba? Meron kang mga bits doon, tapos meron kang quantum gate, logic gates, no? May mga logic gates ka, andun yung OR, yung AND, yung NAND, yung XOR. So may mga ganun ka. Parang ganun din, analogously, parang ganun din yung quantum gates, no? So basically, ang quantum gates change the state of qubits. Halimbawa, ito, ket 00, okay? Pag pinasok mo siya, when you apply a quantum gate here, it changes the state of that from pwede ka mag-apply ng superposition dito. Katulad nangyari dito, nagkaroon siya ng superposition. Ang input mo ay ket 00, tapos nag-apply ka ng quantum gate, which later on will be explained in more detail kung how does the quantum gate work, no? Makikita mo dito, ang output niya is 1 over the square root of 2 ket 01 plus 1 over the square root of 2 ket 10. So, ito na yung next state mo. Okay? This is the next state. And then you can, in series, you can apply another quantum gate here. Okay? So, parang isipin nyo, parang ganun din sa logic circuits, di ba? May mga bits ka nga lang, tapos may mga logic gates ka. Ito naman, mga quantum gates. When you apply a quantum gate, pwede siya mag-result sa ganito state. 1 over square root of 2. Ito kasi mga possible states na pwede siyang karoon, no? 1 over square root of 2, get 0, 1, plus 1 over the square root of 6, get 1, 0, plus 1 over square root of 3, get 1, 1. Okay, halimbawa, this is a sample computation. And then yung lastly, pwede mo siyang i-observe kung ano yung ano. So, ito na yung final result niya pag in-observe mo siya. Okay? So, basically, titignan natin dito, ibig sabihin itong quantum state na to, kasi these scalars, they are called probability amplitudes. Okay? And basically, nagre-represent din sila ng probability. Pero kasi kailangan sa probability, ano yung ating criteria for to make up a probability distribution?
Should equal to 1.
Should sum to 1 and the value should be any number between 0 and 1, di ba? So, ayan, pasok naman. Pero, pag sinam natin to, this is not equal to 1. So, probability amplitudes kasi ito. Para to get the probability, we need to square them. Okay? We need to square them. So, square mo to, this is 1 half. Square mo to, this is 1/6. Square mo to, this is 1/3. 1 half plus 1/6 plus 1/3 is equals to 1. Okay? 1 half plus 1/6 or 3/6 plus 1/6 plus 2/6 equals to 1. Okay? Tapos, meron tayong para pag ino-observe na natin o pag measure na natin yung system na yon, deterministically magko-collapse siya sa isang value. Okay? Magko-collapse siya sa isang value. Pero this is one possible value na lumabas. Pero ang tingnan mo 1/3 lang. So we need to run the computation several times for reliability. Kasi probabilistic nga eh. Pwede kasi mangyari when you observe, ang lalabas dito most likely is 0, 1. So if you run this sample computation 100 times, roughly lalabas 0, 1 will roughly, 0, 1 siguro lalabas siya mga 50 times, no? And then si 1, 0 mga 17 times. And roughly si 1, 1 lalabas siya 33 times. So yung computation, you can run them several times. Tapos, you can get the probability distributions of each of the states. Kung, Any question at this point? Okay.
How do you get the final value based on the probability?
This one? Yeah, merong mga Python programming packages na that you can use to... Okay, the question was, how do you get the final value? So, may mga Python programming packages na, parang ito, may na-observe or measure, yung iba measure yung ginagamit, tapos lalabas na, co-collapse na. And then, meron pa nga silang, parang visualization na, may frequency diagram lalabas yung mga state na yan. And then, magkakaroon ka ng, bar graph, parang ganun sa Python programming. And that's going to be discussed tomorrow, yung sa Python programming na part. But basically, we take advantage of yung quantum mechanical properties of phenomenon para gawa ng computation yung So if we want, for example, so this is just a simplistic na pero pag na tayo ng mga algorithms, we're going to employ a lot of these and probably more qubits din, di ba? Parang so imagine niyo parang lang abstraction lang tong inaano ko, like for example pag nagdi-discuss ka rin naman ng classical computing, yung nasa bit level lang yung dinidiscuss natin. So in the same way, what I'm describing here is just the parang paano ginagawa yung computation and the mathematical representation. Okay. We need to run the computation several times, siguro mga 100 times, no? Pero tingnan natin later, bakit kailangan hindi ba parang siya magastos. Pero in the long run, kung titingnan natin kapag yung complexity ng mga algorithms, no, if you're going to employ this later on, I'll show you mas okay pa din to, mas exponentially, mas okay pa rin gamitin yung quantum computing in some of the algorithms. I'm not saying all of the algorithms mas okay gamitin si quantum computing. Pero in some of the algorithms na ginagamit natin ngayon, theoretically, mas optimal pa rin ang quantum computing. Okay, now, speaking of mathematical representations, so itong mga states na to, like, nabanggit ko that mathematically, we can represent them as vectors. So, very important sa concept ng math for quantum computing, yung concept ng vectors, no? And that is the gist of my talk today. Tomorrow it's another a branch of mathematics yung i-discuss ko, or another area of mathematics. But this time, I'll concentrate on vectors and matrices, no? So, yeah. Vectors and matrices. Yung kaninang binanggit ko yung quantum states, no, or yung qubit, no, we can represent them as vectors. Yung ket0, pwede natin siya i-represent as quantum vector 1, 0, and yung ket1 as 0, 1. And then you can see that all of the possible quantum states, no, yung superposition nito, pwede natin gawin ito yung ket0, ito yung ket1, no, dalawang states or any linear combinations nitong mga to. Okay, so basically we can represent the quantum states as a vector, specifically a unit vector. Okay, so gagamit tayo ng unit circle. Okay, gamit tayo ng unit circle. So basically, ito kunyari yung plane natin. Kunyari, we can represent this unit circle. Ito halimbawa, since this is 1, 0, nandito siya. Okay, 1, 0 yan eh. So, ito siya. And ito yung ating ket1. Okay, so yung superposition, ibig sabihin, quantum state can be represented as any vectors here in the unit circle. Unit circle, kailangan ma-maintain natin yung length na 1. Okay? Yung length na 1. So, quantum state or quantum bit, no, is superposition of this parang ket0 and ket1. So, pag magre-represent tayo ng quantum state, pwedeng ganito, halimbawa, no? Halimbawa, ito. This one, this vector, okay? Papansin natin, ito, this is your alpha, and ito, this is your beta. This one is your beta. This is your alpha, and this is 1. Okay, this is 1. So we have to make sure, by the way, I forgot to say something about the concept of vectors, no? I'm sure meron na kayong idea. When you hear the word vector, narinig ko siya sa physics first yata, no? It's nung fourth year ako, when I was in fourth year high school, the term vector is used to parang quantify or describe quantities that has magnitude and direction. So, meron siyang magnitude and direction. So, I need to write that. Magnitude and direction. Okay, examples ng mga physical quantities. You have velocity, you have displacement, you have force. Those are example of vector quantity, no? And geometrically, we represent them, di ba, as arrows in a complex plane. If you want to, another important, that's the physical interpretation. But we can also think of vectors in the computer science way. No, sa computer science, sometimes yung vector as a data structure, we can see them as just an array of numbers, no, ordered array of numbers sa computer science. So that's the computer science perspective. Pero how are we going to relate them? Okay, we can relate them, di ba, usually sa physics, inaano natin. In physics, we represent vectors as arrow. Okay, tapos ito yung tail, ito yung head. Tama ba? Oh yeah, this is the tail, this is the head. Tapos yung length niya, basically since it has magnitude, yung length nitong arrow na to, yung magnitude, and then yung direction niya, kung yung direction, kaya ito, pwede ka maglagay dito ng angle, for example, theta, no? So that's the direction of the vector. Pero, as you can see, itong point na to, itong vector na to can also be represented by a number. Like in this case, itong vector na to, this vector, for example, is the 0, 1 vector. So you can see this is also an ordered pair, di ba? We can extend this to several dimensions. You will have a series of numbers then, an n-tuple. So basically, yun yung kumbaga connection nung vector na interpretation natin sa physics and yung vector interpretation natin sa computer science. It just tells you kung saan nag-end yung head nung in a conventional parang reference system or Cartesian plane, no? So pagka higher dimension, you're going to have several numbers here. But basically, when you say vector, it's just in computer science perspective, it's just a series of, or a tuple of numbers, no? Pero yung bawat number na may mga ibig sabihin. Like for example, in this case, the first number is yung direction niya sa horizontal, and then yung second number is yung direction niya sa vertical. So dito, pwede mo i-represent yung vector as a point in space. Okay? But abstractly, in mathematics, a vector is anything that you can add and you can multiply by a scalar. Anything at tapos ang resulting product or resulting sum, no, ang result nun is also a vector of the same kind. An example is is a polynomial. A polynomial is a vector because, for example, a polynomial in let's say fifth degree, okay? Because ang criteria lang is kapag ka-inadd mo siya, it's also a vector. So when you think of two polynomials, when you add them, it's also a polynomial. And when you multiply that polynomial with a scalar or with a number, it's also a polynomial. Another example are matrices. Matrices, not same dimension. Because you can add matrices, ang resulting sum is also a matrix. You can multiply a matrix by a scalar. That same then. So matrix, polynomials, those are example of vectors. Yes.
Dapat closed siya.
Closed. Closure property. Yeah. That's the properties of vector spaces. No? Meron siyang scalar multiplication at saka vector addition. Dapat close siya. Like for example, a halo-halo is a vector. Like if you have two halo-halo, pag inad mo sila, pinagsama mo, halo-halo pa din yan. Okay? Ang halo-halo may mga components yan. May mangga, may saging, may langka, may yelo, may asukal. Kung may isang halo-halo, ganun din, may mga components. Pag pinag-add mo sila, halo-halo pa din yan. Kaya tama yung sinabi mo. Closure properties. So anything, any object, anything abstractly na pag pinag-add mo, it's still the same thing or pinag-determine scalar. Okay? We're going to talk about vectors in more detail sa upcoming lecture series. Marami pang mga ano yan. But in this case, siguro ang gusto ko lang i-emphasize sa isang property ng vector is yung magnitude. Or sometimes yung length. Or sometimes ito yung term na norm. Pare-pareho siya. They are synonymous. Magnitude, norm, and length. And tomorrow, when I discuss complex number, lalabas ulit yan. Yung concept ng absolute value. Kaya okay, sige. So, important property ng vector is the length of a vector. Okay? Ito, symbolized by this. Yung norm, kaya you have a vector V is equals to AB. Ito yung dalawang component niya ng vector, no? So, the length of it is just the square root of A squared plus B squared. Okay? So, in this case, ito yung component ni, ito, kung this is alpha and beta. Itong vector na to. Alpha, beta yung component niya. So, sabi dito, all quantum state vectors have a length of 1. Yun yung isang kailangan natin i-preserve. All quantum state vectors have a length of 1. So, ibig sabihin, compute the length of this vector, kailangan natin na, sige dito ko nang ilagay, sorry, yung alpha squared plus beta squared is equals to 1. Okay? So ito, this is your alpha, this is your beta. Kaya nga, it's represented by a unit circle. Any vectors here are valid quantum states. No? Basta, kasi 1 yung ano niya. Okay, now, so that's the norm. And that's the norm or the length of the vector. Let's extend that to higher dimension. Kung ito sa 2 dimensions lang, we can represent. Pero, what if, yung kanina example ko, what is pag 2 qubit states na? So, we have 4 states, di ba? So, ito yung vector representations ng mga states na yung pag 2 qubit na. Yung, kanina, di ba, yung 1, 0, sorry. Ay, etong ket 0 is 1, 0. Yung ket 1 is 0, 1. Okay? Now, pagka 2 qubit states na, so, ito yung mga different states. 4. Kasi 2 qubit, 2 raised to 2 squared, no? So, that's 4. Ket 0, 0, ket 0, 1, ket 1, 0, and ket 1, 1. Okay, ito yung ket 0, 0, 1, 0, 0. Ito, ket 0, 1 is to 0, 1, 0, 0. Ket 1, 0 is 0, 0, 1, 0. And then ket 1, 1 is 0, 0, 0, 1. Now, paano natin, geometrically or graphically, how can we represent this? This is already in 4 dimension. It's really hard. Kung 3, pwede pa. You can represent pagka, yung 3 stages lang. Pero pag ito kasi, 4 na dimensions na. Ito kasi, each one of these, like for example, parang natural basis siya, no? Yung concept ng basis, I'll discuss that later on, no? But basically, ang ibig sabihin lang ng basis na pwede mo siyang gawing axis dito, and then you can generate the whole orthonormal basis sila, orthonormal basis. Orthogonal sila, and then they have a unit length, no? They have a unit length, tapos orthogonal sila. Pag sinabing orthogonal, they are at right angle. Okay? They are at right angle. And basically, kakagawa ka ng parang ganito unit circle. So dito, you can represent this as a parang unit hypersphere. No? Sphere na siya. And then, sobrang dami ng, ng vectors that you can. Kumbaga, yung vector that, na representation nito, parang isang arrow dun sa unit sphere. Okay?
So you can represent more information.
Yeah. Yun yung point. We can represent more information. But pag dumadami yung ating qubits, mas maraming information tayo mare-represent. Kaya nga yung race nila ngayon sa mga quantum computer, pataasan sila ng dami ng qubits. Hindi ko alam kung kung yung sa Google or yung sa ibang companies kung ilang qubit na yung kanilang quantum computers. Pero yun yung idea. But we have to, syempre, para ma-understand natin yung basic at saka yung foundation concept, we would start with yung mga 1 qubit and 2 qubit systems muna. Okay. So, eto yung representations kapag 2 qubits na. And then, you can probably, based on this, you can probably tell na kapag paano pag 3 qubits na, dali na lang yun. Okay? Yung representation. Ito yung para magiging basis mo to actually come up with the other vectors in 2 qubit system. So basically, that will just be a linear combination of any of these 4 states. And paano pala natin i-compute ang length? By extension, the formula for the norm of the vector is equal to, kunyari kung ganito na 4 na yung dimensions, ganun din, square root of a squared plus b squared plus c squared plus d squared kung ito yung vector. Okay? So, nang mention yung term na orthogonal at saka yung normal or yung orthonormal, pag sinabi kasi orthogonal, ibig sabihin, they are at right angle. Pagka normal naman, orthonormal, ibig sabihin, parang their length is or magnitude is equals to 1. Yun kasi yung kailangan natin i-preserve. All quantum state vectors have a length of 1. So, kailangan natin masatisfy ito dun sa ating mga quantum computation. Question, why is it important na dapat length is equals to 1? Tingin niyo, bakit kailangan natin ma-preserve yung unity? Anyone?
Pwedeng joke.
Ha?
Because it's probability po.
Yeah, it's somehow related to the probability interpretation, no? Na 'di ba, ang probability natin, that's one of the reasons why we need to preserve yung length ng 1 kasi nga probability, 'di ba, pag sabing probability, it should sum up to 1. Okay, so what else did I miss? Yung norm, concept of a vector, the length is equals to 1, the norm, tapos paano na kapag more than that 2 dimensions. So balik tayo dito sa So kung kailangan natin ma-preserve pala yung 1, okay? Kung para ma-preserve, tingnan natin itong sample computation ko. No? Ito 1 over square root of 2, 1 over square root of 2. Tingnan na nga natin kung this is a valid transformation, no? Tingnan natin yung 1 over square root of 2. So, let's say, alpha is equals to 1 over square root of 2. And your beta is equals to 1 over square root of 2. The length of this should be square root of 1 over square root of 2 squared plus 1 over square root of 2 squared. So, ito ay square root of 1 half plus 1 half equals square root of 1 equals 1. Okay, check. About this, tingnan natin kung valid to. Tatlo. 1 over, actually, apat yan. 0 lang yung isa. Okay, apat yan. Yan ang 0. Dito kasi dalawa yung 0. Okay. Pero apat yan since we're working with 2 qubit states. Okay, square root of 2 squared plus 1 over square root of 6 squared plus 1 over square root of 3 squared. Okay, square root of 1 half plus 1 over 6 plus 1 third equals to square root of 1 equals 1. Okay. So dapat ma-preserve lang yung length ng quantum vector. So, ano naman tong mga quantum gates na to? Yung quantum gates na kung may mathematical representation natin, kung ito ay mga vectors, these quantum gates are matrices. Okay? So, para magkakaroon tayo ng matrix vector multiplication. So, ang nangyayari dito is just a vector matrix, a matrix vector multiplication. And I'm sure a lot of you are familiar on how to do matrix vector multiplication. Other term, you can also think of matrix multiplication as a linear transformation. Kasi yung sa space mo, pag nag-multiply ka ng matrix, magkakaroon ng transformation dun sa state mo. Kaya lang, dito kasi, ang kailangan na matrices lang. Ang mahalagang matrix na kailangan natin is yung tinatawag na unitary matrices. Unitary matrices. Not just any other matrices. No, unitary matrices. So ito ay this is a unitary matrix, this is also a unitary matrix. Bakit important ang unitary matrix? Kasi ang unitary matrix pine-preserve niya yung not all matrices kasi are length preserving. Itong unitary matrix is a length preserving matrix. Ibig sabihin, pag minultiply niya, transform niya yung isang vector. When I say transform, ibig sabihin minultiply mo siya ng isang matrix. Okay? When you multiply a matrix by a vector, yung length ng vector na yun ay na-preserve pagka unitary yung matrix. Okay? Give an example of a matrix na na-preserve. This one, sa 4x4. This one, sa 2x2. Trivial example ng unitary matrix. What's a trivial example of a unitary matrix? Okay, a trivial example of a unitary matrix is that identity. Okay, preserve niya pa rin yung length eh. Di ba? You have I2 and I4. Sorry. I4. Okay. Identity. Pag minultiply mo yung matrix ng yung vector ng identity matrix, yung pa rin yung sagot. So, na-preserve pa rin yung length. Pero mayroong mga matrices na hindi identity that can still preserve the length. Pero iikot siya. Mag-iiba ng direction. Okay? Yeah. So, these are example of unitary matrices. So, example. Sige, try natin i-multiply. Gamitin natin itong Q. Mamili tayo, let's say, multiply natin yung Q by, let's say, 0. Okay? Q, multiply natin sa ket 0. Ano lang, this is just to test yung, para illustrate ko lang kung paano mag-multiply, no? So, 0, 1, negative 1, 0. So these are the mathematics that you need to understand para ma-gets natin yung mga concepts sa quantum computing. And this one is just a vector of 1, 0. So yung sagot nito ay, so ibig sabihin, when you apply this transformation dito sa ket 0, anong mangyayari sa kanya? Paano ba mag-multiply? Ito muna, di ba? Tapos ito. Tapos, ang sagot nito, this is a 2 by 2 matrix. This is a 2 by 1. Tingnan natin kasi hindi tayo basta-basta nag-multiply ng matrices. Dapat kailangan yung dimensions sila ay compatible. Paano natin malalaman kung compatible? Kung yung columns nitong nasa left mo is equal to the column to the rows, number of rows na nasa right mo, compatible sila. So in this case, compatible sila. Ngayon, ano yung magiging resulting dimension nung product mo? The resulting dimension would be this one, 2 by 1 din. So, ibig sabihin, 2 by 1 din yung magiging sagot mo. Okay? So, pero, ano yung ilalagay natin dito?
May question pa ba?
So, first element would be yung first row nito, tapos ito. 0 times 1 is 0. Negative 1 times 0 is 0. So, this is 0. And then, to fill this out, ito naman, 1 and 0. So, 1 plus 0 is 1. So, ito yung sagot. So, nangyari, when we apply the transformation or when we multiply the matrix Q with ket 0, ang lumabas ay 0, 1, which is equal to this one. Which is equal to ket 1. Okay? So, anong nangyari? Pinalitan, ayan, parang ang nangyari dito, ito, itong itsura na to, na matrix na yan, ang effect pala niyan dito ay yung nandito, lumipat dito. Diba? So imagine niyo yung multiplication ng matrices, it's just like parang winawarp po yung space kung nagkakaroon ng rotation. Pero dapat mape-preserve pa rin yung length. Yun yung importante. Kasi generally, ang matrix multiplication, nagkakaroon siya ng linear transformation. But not all of them nape-preserve yung length. Pero may mga matrices na nape-preserve yung length. Ang tawag doon, yung unitary matrices. Now, as your exercise, madali lang nung kahit hindi na natin exercise. Try natin naman sa apat. 4 by 4. Let's say, okay, i-multiply natin itong u, mamili tayo dito. Dito sa, okay, what will happen if we multiply u by this one? Mentally. Ito yung u natin ha. Pakitutok na lang yung camera dito. Ito yung u. Tapos multiply natin sa 1, 1. Kunyari, u multiply natin sa 1, 1. Sagot dito ay, tingnan mo to, 1, 1 niya is puro 0 eh. Diba? So, mangyayari dito, kung puro 0 yan, andito yung 1, 1 mo. Multiply mo. 0, 0, 0, 1. Okay, ito magzi-0. Ito magzi-0. Ito magzi-0. Matitira lang ito. Parang kokopyahin mo lang to. So, the answer is 0, 0, 0, 0. Okay? Pero pag minultiply mo naman siya sa 0, 1, let's say 0, 1. Okay? 0, 1, ito naman siya. Okay. 1 ito. Ito ay 0. So, yung second row yung kukunin niya. Ito kasi 0 to. Dahil mamumultiply siya dito. Ito mamumultiply siya sa 1. The rest mamumultiply niya sa 0. So, kapag minultiply natin sa 0, 1, that's going to be this one. 1 square root of 2, 0, negative 1 square root of 2, at saka 0. Okay? So, ayan. Ito yung mga pag-aaralan natin sa mga susunod na lectures, no? Matrix multiplication, yung concept ng unitary matrices, vector spaces, ayan. So, that's why it's important na alam natin sila. At ma-practice natin sila. Ma-practice natin yung matrix vector multiplication. Because essentially, what we're doing in the computation is just matrix vector multiplication. Okay, wait lang. Pansin nyo, ito, may negative. Pwede ba yun? May negative? Kala ko ano? May negative. Akala ko pa probability. Pwede. Kasi what we're talking about dito, ito mga coefficient na yan, they are probability amplitudes. They're not yet probability. You can square them. But you can square them, or alam nyo ba, na hindi lang negative, hindi lang di ba marami tayong mga numbers, we have the integers, rationals, irrationals, and then all of them are real numbers. Actually, we can have complex numbers as amplitudes. We can have complex numbers as amplitudes. No? So, I'm going to discuss tomorrow yung complex numbers. Okay? Pero, the important thing, para ma-compute natin siya sa yung probability amplitudes into probability, we need to get the absolute value and then squared para maging probability siya. And then, kung madami yan, we have to take all of them together and then get the sum. Like in this case, absolute value of 1 square root of 2 squared plus 0 squared plus absolute value of negative 1 over the square root of 2 squared plus absolute value of 0 squared. And this should sum up to 1. Okay? Any question?
Clarification.
Yes.
Yung kanina, when you multiply the u by ket 1, 1, di ba dapat 1, 0, 0, 0?
Which one? Sorry?
Yung u by this.
By this? U. By
Ket 1, 1.
ket
Kasi
1.
dapat di ba 1 yung magnitude niya.
Okay, let's do that. U by 1. Okay, try natin. Let's do that.
Ket 1.
That's 0, 0, 0, 1, di ba?
Ah,
So this one,
times
okay,
1,
tama.
0, 0, 0.
Yeah. Sorry. Good point, sorry. I need to clarify pala yung multiplication ko kanina. Okay, so U multiplied by ket 1, 1, for example, so mangyayari, sige, gawin natin yan. Let me just get my razor. To illustrate matrix vector multiplication, thank you. Sige. So this is our U and this is our 1, 1. Dito ko na lang ilalagay yung sagot. This is a 4 by 4. This is a 4 by 1. So, ang sagot, compatible sila. Okay? Pero yung sagot niya is 4 by 1. We need to fill this out. Okay? So, para dito, sa first na i-multiply natin to. Since 0 naman ito, magiging 0 na to. Di ba? Tama?
Opo.
0. So,
Ano magiging 1 siya?
oo. Sorry.
Kasi may 1 kasi dito.
Yeah. Yeah. Thank you. Mali yung ko. Okay. Linear combination nga pala. 0 times 0 plus 1 times 0 plus 0 times 0 plus 1 times 1. Thank you. So the answer is here is 1. Okay. Next. Ito naman. To illustrate matrix vector multiplication, this is our matrix, this is our vector. 1 over square root of 2 times 0 is 0. 0 times 0 is 0. Negative 1 over square root of 2 times 0 is 0. 0 times 1 is 0. So, i-add mo lahat yun. Since all of them are 0, 0. Okay? Hindi ko na siya in-expound, ano? I hope you're getting yung ano, in your head, no? Pero ganito lang naman siya. Kunyari, ito, fill up natin tong third element of this 4 by 1 vector. 0 times 0 is 0. Plus 0 times 0 is 0. Plus 0 times 0 is 0. Plus 0 times 1 is 0. So, all of them are 0. So, 0 to. Okay? And then, last one, 0 din to lahat. 0 to. So, ito pala yung sagot. Ano ba yung sagot ko kanina ulit?
0 lang.
0 lahat? Oo.
So, dapat magnitude is 1, di ba?
Okay. Good. Good catch. Okay. So, ito yung sagot. Pag minultiply natin, CU by ket, ano yun? 1, 0? 1, 1. Okay. Yun yung ating matrix. So, itong matrices na to, itong mga gates na to, as you can see, quantum gates change the state of qubit. Parang ganun yung ginagawa. Itong mga quantum gates. So, from a single state, nag-apply ka ng quantum gates, effectively, parang ginagawa natin, minumultiply natin siya ng matrix. So, nababago. Okay? So, parang nangyayari dito, ito, nag-apply ng gate, nag-transform siya, napunta dito. Okay? And nag-transform na naman, napunta doon. Okay? Parang ganun. So, ganun yung nangyayari kapag nag-apply tayo ng quantum gate. So, that's why it's really important for us to know a little bit of linear algebra. This actually is parang under linear algebra. Okay. Any question? Thank you for the clarification. Nalito na ako dun sa ano. Pero that's good point kasi na-illustrate ko kung paano mag-multiply ng matrix at saka vector. Which is very foundational pagdating sa quantum computing. So, tomorrow, sabi ko nga kanina, meron kasi tayong yung mga numbers dito, yung mga numbers na yan, they can be complex numbers. And that's my topic for tomorrow. I'm going to delve on the arithmetic of complex numbers, addition, magnitude, and so on. Yung complex plane, and then representations, yung polar, at saka yung exponential representations ng complex numbers. Kasi ito, dinescribe ko yung mathematics of quantum computing using vectors and matrices, no? Na without the complex numbers involved, no? Pero later on, tomorrow, are going to involve complex numbers na. Kasi sabi ko nga, itong mga numbers na to, they're not just real numbers, they can be complex numbers. Okay, so, anong importance nito? I mean, nitong quantum computing in general, based on what I have discussed so far. So, I'll just delete this. Kaya halimbawa, meron tayo. Ito kasi parang simplification lang, parang 2 lang. Pero what if you have, for example, let's say 6, no, qubit state, 6 qubit state systems. Nag-apply tayo ng gate, halimbawa. So, nag-apply tayo ng gate dito, ng transformation, nag-result siya into, let's say, C1 times, lagyan mo na lang 6 6. Ibig sabihin itong 6 na to, this is a number, parang one of the 64s. Kasi you are going to have 64 states Plus C2, 6 na lang. Plus, halimbawa, yan. Or kung ilan man yung C3, 6, Cn. Okay? Parang ganito lang nangyari. Okay? Ito, dalawa lang. Some of this may 0, hindi mo naman kailangan this should be 63. Ah, 6. Let's start with 0. Okay. Okay. C0, Z1. Okay. Some of ang C pwede maging 0 ang value. Okay? So, nag-apply tayo ng gate, tapos ito yung naging superposition siya nito. Okay? Itong ganito natin is just one of the 64 states, no? Yung 6 na yan. And then nag-apply ulit tayo ng gates. Will result to the same thing. Let's say, siyempre ibang values na yan, no? C, D, let's say D naman. D1 6 plus D2 6 plus D63 6. Okay. And then sa dulo nag-observe tayo. And then may lumabas na yung gusto natin maging sagot. Okay? Which is, halimbawa, from there, naging ganito siya. Nag-collapse na siya sa 0, 0, 0, 1, 0. Hindi, ito na lang. Para simple. Yan. Ito na yung final state. Okay? So yan, we have a series of, this is a computation, a sample computation. And we want this. Okay? Ngayon, imagine ninyo, ito, ginagawa to ng quantum computer at the same time. Ito, ilang steps lang to. Let's say, for example, ito lang. Isa pa, kunyari maglagay pa ako dito. E1 plus 6 E2 6 E63 6. Okay? Then observe. Okay. Etong quantum computation na to, yung quantum computer, ginawa nilang to ng 1, 2, 3, 4 steps. Okay? 4 steps lang. Pero, pag classical computer ang ginamit mo dito, it could involve 1,000 steps. Bakit? Kasi sa quantum computer, it can track of the different states at the same time. Parang nagpa-parallel com. Hindi mo nga lang siya mini-measure pa dito, pero it is tracking yung mga states na yon all at once. Yung 64 states na yan, it's tracking at every step. Pero, the way, if you're going to implement this in a classical computer, hahanapin niya para makareach siya dito, tatry niya yung mga possibilities. Ito, that's one. Ito, or dito, tapos dito. So, imagine niyo combinatorial explosion. Yun yung dami ng steps bago mahanap if you're going to use classical computing. So, that's the major advantage. Well, that's one of the major advantages of quantum computing. Yung mga ganitong computation. Kaya it can speed up the computation exponentially. Kasi in quantum computing, it just takes 4 steps lang. Pero in classical computing, hahanapin niya kasi isa-isa yung state. Kasi 'di ba isang state lang ang kaya niyang i-track at the same time kasi bit nga siya. Since we're using the concept of superposition, kaya niya yan sabay-sabay. So 4 steps lang. Parang yung kailangan mo, 'di ba? Algorithmically na minimize mo ang laki by exponential yung savings mo in terms of the number of steps. 'Di ba? Kasi ito pag nag-classical ka, try mo dito, try mo. O pag hindi mo nakita 'yon, try ka ng isang path. Okay? Dito, ganon. So combinatorial yung explosion. And this is how many? 64 times 64 times 64. How many is that? Diba? That's 2 raised to the 18th. Okay? 2 raised to the 18th. So, ganun kadami yung Pero ito, 4 steps lang. Diba? So, yun yung advantage ng quantum. Yun yung promise, yun yung potential ng quantum computing kapag nag-implement natin. And one of the, parang isang famous algorithm, yung Shor's algorithm. Yung Shor's algorithm, ginagamit nila sa pag-factor ng large numbers. And one of the applications kasi ng factoring of large numbers is in cryptography, di ba? Imagine niyo yun. Sa Shor's algorithm, it take advantage of this, of quantum computing. Theoretically, pwede pag na-implement siya, ang laki ng speed up in terms of the algorithmic complexity. So that's one of the major advantages of quantum computing. And with that, I hope I was able to whet your appetite to learn more about the mathematics of quantum computing. And see you tomorrow for my discussion of complex numbers as it relates to quantum computing. And also, we're going to implement this with the help of one of our lecturers, no? Python programming naman. Yung kaninang question, paano natin i-implement to sa Python programming. So may mga no. So I hope you stay tuned for tomorrow's lecture. And with that, good afternoon and Merry Christmas. All right. All right. Thank you for listening. And I guess now it's time for the open forum. I see there are some questions already in the chat box. Thank you for listening. And by the way, I'd like to thank my colleagues who helped me to come up with that video lecture. Si Ethel and si Tony, kasama ko sila ngayon dito sa office. Thank you. And they're also, thank you for joining Tony and Ethel. Yeah, let me check yung chat box for the questions. And tomorrow, meron pa tayong continuation. I'll be talking about other mathematics involved, no? Let's see here. Let me just check. So my question here, how are the probability amplitudes identified, pre-selected or each state, or randomly generated for each state? If randomly generated, what principles govern the assignment? Okay, good question. So remember yung kanina when I talked about the computation, the idea there is you're going to design a circuit, a series of gates, no, computation. So you're going to design a circuit, and at the end, you wanted something na an output already. So basically, by design, you should design a gate that would somehow make sure that the correct answer that you're trying to output will be the most probable one. Because as I mentioned a while ago, you already know the output is just that you have to tip the scale so that when you design the circuits, that answer would be that quantum state would turn out to be the most probable state in your circuit design. Yes, probabilities are assigned by the gates applied to the qubits. Yes, and what else? Okay. Are there any other questions? I hope I was. Perhaps my other colleagues can chime in to answer that if my answer is not, or they can provide other information. And with that, yeah. Thank you very much again, and good evening.
Awesome. Thank you po for that wonderful pahapyaw kumbaga, no. It might sound na marami tayong iniisip and there's a lot of math around it, pero as we can see, there's really the fundamentals really yung nag-shine through, and that we just need to scale it and solve for bigger matrices, and yeah, as we apply different gates. So konting ano rin, actually you can represent the gates as their own matrices, and then you just apply like multiplication all over again, and you can measure at the end to get your answer. So yeah, thank you for that, Sir Elmer, for the very wonderful video and answering our questions. Okay, Sir Bob, do you have anything to say po?
Wala na, okay na.
Awesome. Okay. So at this point, I would like to ask everyone to please turn on your cameras and let's take a photo. Yay. Ayan. So how was the first session for tonight, for today? Ayan. Hello, hello. There's still some people at the office. There's one at the forest. Nasa forest na po ata siya. Nagbabakasyon na. Hello po. And yeah, some of them, yan, nasa door, nasa bahay. Ayan. Hopefully you're comfortable there. So hello, hello. Hi, hey, my baby. Hello. So cute, so cute. Hello po. Ayan. Okay. Okay, so if you can turn on your cameras, you can react a heart so that we can feel your presence. Okay? Hello, good evening po. Okay, I'll take the photo. One screen lang. One, two, three, smile. Okay. Another one. One, two. One, two, three, smile. Alright. Okay. Alright, thank you for your participation at this point. Yeah, at this point the our session is now done. So I you can answer this attendance form, and yeah, I just sent it on the chat box. Okay, so to close in on our there's just some questions to ask if there's some things that are still unclear to you, so that uh we can answer your questions tomorrow and on how the things go. So yeah, for now, oh wait, sorry. Let me open that. Wait, let's try. Wait, okay. This is second po. Ayan. So we're actually using our QCSP email now. So yeah, let me turn it from the. Oh yeah, and there we go. You can you can refresh and try again pa. Okay. Can you give me a heads up if okay? Wait, okay, I think it's okay now. Alright. Okay. So yeah, if yeah, you can answer the form, and then you can have a nice dinner na. Thank you po again for being with us tonight, the first session of our Busu Quantum Leap program, and we'll see you tomorrow. Ayan, thank you very much po.
Bye-bye.
Thank you.
Thank you. Bye-bye.
Thank you. Thank you po.
Thank you.
Recording stopped.